Good morning, and welcome to another fun-filled day of 307, summer edition, learning material balance and lots of wonderful things associated with material equilibriums and considering multi-phase, multi-component systems, which we'll get to next week and the week after. But today, we are looking at, hopefully, finalizing content for Chapter 4, which is the bulk of just material balance fundamentals, looking at reactive combustion material balance problems and how to analyze systems when those reactions and combustion processes are present. So I'm going to flip it over to the notes. Before I kind of start jumping in, are there any questions, comments, concerns? One thing I do have to add is your homework 3 is due tonight at midnight, and I believe quiz 3 is due on Sunday night at midnight. So please make sure that you get those in on time to receive credit for those assignments. All right. So last time, we were talking a lot about combustion reactions in material balance problems. And we discussed looking at combustion systems in terms of both complete and incomplete combustion, where let's say we had, what do we want to burn today? C2H6, I think that's ethane to make CO2 and H2O, or if we have complete combustion, and when we have incomplete combustion, in lieu of carbon dioxide formation, we have carbon monoxide formation. All right, I can probably balance this, hopefully without too much trouble. No, never mind. That's a 3. 7. And so depending on the concentration of oxygen will largely determine the selectivity of complete versus incomplete combustion. You know, where oxygen is typically fed into our process via air, where we said air being 75 mole percent nitrogen, 21 mole percent oxygen. Also, FYI, the molecular weight being 29 grams per mole. That's the best value to use for calculations when it's necessary. We also talked about a wet basis versus dry basis, where let's say if we have 100 moles of air, or should I say of wet air, that's 8% water. And I want to know what's the actual compositions of nitrogen and air, or nitrogen and oxygen. Well, if basically that means I have 91 moles air, if I can do math, sorry, 92 moles air, 8 moles water. So if you do the basis on the dry basis, you'll still see that 79% nitrogen, 21 mole percent oxygen. And on a wet basis, those values will be lower, right? Because we only have 92 moles of air out of the total 100. So if I wanted the mole percent of nitrogen and oxygen on a wet basis for nitrogen, it would be 79 of the 92 out of 100. And for oxygen, it would be 21% of the 92 out of 100, which would be 72.7 for nitrogen, and for oxygen, 0.193. I know I'm going a little quick. I want to get to some problems today, but I do like doing recaps because I think it helps kind of wake the brain up and be like, oh yeah, I remember that. Are there any questions on some of those concepts? No? All right, I think the last concept we talked about was excess air and combustion, where in order to ensure that our fuel is our limiting reagent, we make sure that air is our excess reagent, and we can essentially analyze things in terms of the fractional or percent excess of air, where if I wanted the percentage of excess air, it is the moles of air fed minus the moles of air needed. I shouldn't say stoichiometry because air isn't in the stoichiometry. Over the moles of air theoretically needed. Times 100. I do want to point out here, I think when I first posted this lecture on the Blackboard site, this was written incorrectly, but I did correct it and re-upload it. But just double check the notes, or if you downloaded it last week, it should be fed minus theoretical over theoretical. And that gives you the percent excess air for the system. And one other thing that we also like to think about is quantifying things in terms of an air to fuel ratio. And this can be by mass or by mole, meaning we can have a mass basis for the air to fuel ratio or a molar air to fuel ratio. And I can simply define that, the air to fuel ratio of the molar basis. I'll put as much detail as I can. It's just the moles of air and fed over the moles of fuel fed. And then for the by mass, it's just the mass of air fed over the mass of fuel fed. which if I want to convert between the two, right, fuel mass is just simply the air to fuel molar times the molecular weight of air over the molecular weight of your fuel. And so there's a lot of ways in which we can describe and denote information in a material balance type problem involving combustion. So let's look at an example, because the best way to learn these things is to practice applying it. And so we're going to say propane is burned with 40% excess air. And if 90% of the propane is burned, with 15% of that reacting to form CO with the balance. The balance forms CO2. Let's estimate the composition. Of the output stream. So first thing I would probably want to do, as always, is draw my flow chart and do a degree of freedom analysis to see where I stand. Well, my process is going to be propane burning C3H8 plus O2 yields CO2 and water, and C3H8 plus O2 yielding CO and water. So the first step we're going to look at here is balancing those chemical reactions. So doing a carbon balance, I need a 3 here. I also need a 3 here. Doing a hydrogen balance, I'm going to need a 4 here and a 4 here. Now for my oxygen balance, I have, let's see, 10 on the right. So I'm going to need a 5 here. And for the incomplete combustion, I see, let's see, 7. So I need 7 halves here. So I have C3H8 being fed into my process. And I also have air, which is 79 nitrogen, 21 oxygen. And leaving the process, I have C3H8, air, CO2, CO, H2O. Once again, 0.7. You really don't know the composition, you just know oxygen's being consumed. So that composition in terms of is really unknown. So if we were going to do a degree of freedom analysis, how many unknowns do we have? Well, for this, we have quite a bit of unknowns. Primarily because we really don't know any of the molar flow rates coming out of the system. Now, we do know that our conversion is 90 of the flow rate of propane coming in. We know the percentage of excess air coming in based on the problem statement. And we know that 15% goes to CO. So that gives us 3 relations. But in terms of the unknowns, we have, let's see, we have 6 unknowns that I see, which is essentially all of the flow rates leaving, what else? Now, this is where it can get a little tricky. If I really think, I don't know the flow rate coming in or the flow rate of air coming in. All right, so it really looks like 7 unknowns, right? But I can take a basis for this problem and reduce that to 6. And so if I take a basis probably of my fuel coming in, I can reduce the number of unknowns. I have two reactions and 3 relationships. And so an initial inspection gives me that, well, it looks like I have a degrees of freedom of 1. Do you guys agree or disagree with that? You guys not talkative today? All right. I would also, if I know 15% goes to C3H8, I could probably also say, since the remaining goes to CO2, that gives me probably enough specifications that I can more than comfortably change this to 4 and set it to 0 and say that this is solvable. So let's take a look and see if that's right. And I'm going to redraw this with my basis. And I'm going to say my basis is 100 moles propane. And let's see how this changes my problem. Still have those same reactions. And here I'm going to use a different color for the subscripts, 5, 3, 4. It's easier to see them. So in order to get my air feed, I have to rely on the information in terms of knowing that there's 40% excess air. And that should be equal to the air fed minus the air theoretical over the air theoretical times 100. So if I know the theoretical flow rate that's needed, I can find the actual flow rate in my process. So based on the system, what would be my theoretical airflow rate? What do you guys think? This gets tricky, right? Because I have two reactions. Well, for combustion reactions, we're going to rely on complete combustion to determine our theoretical value, which means if I have 100 moles of methane coming in, then I need 500 moles of oxygen for complete combustion. And conversion of my fuel. And since my mole fraction of O2 in my feed is 0.21, that tells me that that theoretical, I'm just going to call it N sub air sub T for theoretical, is going to be 500 moles over that 0.21, or 2,381 moles of air. And that's my theoretical. So knowing my theoretical now, I can plug that back in here to find my actual feed flow rate. Or I can say 40% is equal to NA feed minus 2,381 over 2,381 times 100. So what is my actual air feed flow rate? Well, that should be about 3,333 moles of air. So now I can put that into my system, which tells me with that many moles of air, I have about 700 moles oxygen and the rest nitrogen. Now, the nitrogen doesn't react, so I can just immediately just carry that over and just say in the output stream, I have that 2,633 moles nitrogen. Then the question then becomes, well, how many moles of propane do I have in my exit stream? Well, knowing that my propane conversion was equal to 90%, which equals moles fed, or excuse me, moles reacted over moles fed. That tells me that my moles reacted is 90 moles. And if I react 90 moles with my basis of 100, I should have 10 moles of propane in my outlet stream. Everyone following so far? All right. Now let's see what we can do to find the rest. Let's look at a balance on CO. Well, I know in the problem statement, %15 of the propane reacts to form CO. Meaning my output should equal the generation, which based on that information is 15% or 0.15 of the propane fed based on the stoichiometry, or 100, meaning I produce 15 moles of CO. So I can put that in my process. Now the remaining should go to complete combustion. So now if I look at a balance on CO2, I can say the remainder of propane combusted goes to CO2. Same balance, output equals generation, which equals 0.9 times 100 minus 0.15 times 100. That was the complete conversion minus that which went to CO2, or 90 minus 15, which should be 75 moles of CO2. So now I can put, well, 75 moles of CO2. Oh, excuse me.
I thought only
produces
90% of the propane was reacting, not 100.
It is just 90, but I forgot the stoichiometry. So I have to multiply this times the stoichiometry. Thank you for reminding me. So I forgot that for every mole of propane that reacts, 3 moles of CO2 and 3 moles of CO form. So it should be 3 times the 15% of the, so this should be 45 moles, and this should be 225 moles. So go ahead, Mitchie, repeat your question. Does that answer it, or did you have another question?
No, sir. So I thought only 90% of the propane was reacting. So 10 moles is coming out. So would it be
That's
90
what this is here. It's
times-
90 times 100 minus the 0.5 times the stoichiometry, which is 3. Which should give me 225 moles.
So 15% of the 90 moles reacting creates CO.
I see what you're saying. It's admittedly kind of vague in how it's written. So you're saying you took it as 90% of the propane is reacting. Of that 90%, 15% is forming CO.
Yes, sir.
This was a homework or exam question. As it's written, I would accept either. The way I'm interpreting it in this example is I'm saying 90% of the propane reacts, and of all the propane in general, 15% is going to CO2.
Alrighty, thank you so much.
No problem. I do agree that is, in terms of how I wrote in it, it is kind of vague. All right, so now let's look at, now that we've got CO2 and CO figured out, we can look at the water generated. So let's look at a balance on H2O. Now, I have the same material balance. Output is equal to the generation because there's no water coming in, meaning and for both processes, they produce the same amount of water. So since I have 90% being consumed of the propane, I can just state 90% times 100 times 4, which should give me 360 moles of water formed. So I can go back to my drawing, state 360 moles of H2O being produced. And all I think I have left now is the oxygen, which I have the moles coming in. I can calculate the moles being consumed so I can get the output. So if I was going to do a balance on my oxygen, I would say output equals input minus generate consumption, excuse me. And that equals my 700 moles in minus, well, I've got 15% of that first reaction. With the stoichiometry for that first reaction, I believe was 5. And then for the second reaction, I had the remainder of that, or 0.75 times 100, with that stoichiometry being 7/2, or 3.5. This tells me my output is 700 moles minus 15 times 5, which is 75 moles, minus 3.5 times 75, or 262.5. Which should give me about 362.5 of moles of O2 leaving my process. Are there any questions on that now that I have essentially the molar composition with my basis figured out? So now with that in mind, I can add up and determine my total moles in my output, which I've got 3,635.5 moles. And if I divide each of these components by the total number of moles, I can get the mole fractions, which we'll put it in red. So 2633. So from that, I have 0.72 N2 0.003 propane, 0.012 CO, .061 CO2, about 0.1 H2O, and 0.1 O2 to give you the approximate mole fractions of the output stream. You notice the majority is still nitrogen, and we have a fair amount of water, oxygen, and CO2. With the propane and carbon monoxide, that could be considered trace. Is there any questions on how I did those calculations? One last thing we can also calculate is the molar air to fuel ratio entering the process. Which, based off our system, we had 3,333 moles of air to 100 moles of fuel, meaning our air to fuel ratio was 33.33. And for fun, if I wanted to find the mass air to fuel ratio, I can just take that 33.33 moles of air per moles of fuel, multiply it times the molecular weight of air, which is 29 grams per mole, and the molecular weight of the fuel, and it's propane, which is 44. So I divide that by that, 44 grams of fuel per mole of fuel. And I'm left with the mass basis of the air to fuel ratio, which is 21.97 grams of air per grams of fuel. Any questions on that example problem? No questions? Let's look at one more example. Let's say I want to look at octane undergoing complete combustion. I'll make this bigger. Yeah, it should be 25. And let's say I'm burning this octane at a rate of 150 moles per hour. And my question is, what is the required airflow rate if I have 98% complete combustion? Meaning my conversion is 98%. Well, that 98% should equal my flow rate fed minus my theoretical over my theoretical. So I have to find the theoretical flow rate of air needed. So for 150 moles per hour of octane, what is my required flow rate of oxygen? Well, I'm looking at my stoichiometry. For every mole of octane that combusts, I need 25 over 2 or 12.5 moles of oxygen. So my theoretical amount of oxygen is my 150 moles of octane times that stoichiometry. For every mole of octane, I need 12.5 moles of O2, which is 1,875 moles of oxygen. To get my theoretical air, I have to take that airflow rate and divide it by the mole fraction of oxygen, or for every 0.21 moles of oxygen is in 1 mole of air. So what I get is about 8,929 moles of air. And that's just for my theoretical amount. Oh, and this isn't excess. This is just 98%. So how much air is needed? That's what's being asked. So this would probably assume no excess air. So we would just be looking at the theoretical, which is just this 8,929 moles of air and the 1,875 moles of O2. Probably wouldn't be super realistic, but that would tell you probably the minimum needed. I was just double checking the wording on that problem. So it's interesting, right? That would be the bare minimum to get this process going. Is just looking at that theoretical requirement. But even then, the molar composition of that fuel in the system, right? If I look at this 8,929 moles per hour as compared to the octane 150 moles per hour, that tells me that for this system, I only have about 1.6, 1.7, it's actually 1.65 mole percent of fuel in my stream, which is extremely low. So an interesting consideration is what would be the limits associated with the percent excess air, or I could ask it this way, what would be the maximum percent excess air in the system if my LFL was 1.4 mole percent fuel. Meaning, if in my process, my octane was 0.014 mole fraction in that feed stream, with the rest being air, what would be the percent excess air? Well, based on our 150 moles per hour, that would make the total flow if the fuel was only 1.4%, 150 moles per hour over the 0.014, that would be 10,714 moles per hour total. Meaning my air would be that total flow minus the 150 moles per hour, or 10,564. So the percent excess that we could have would be that 10,564 minus the theoretical minimum, which was 8,929 over 8,929. Or 0.183 or 18.3% excess. Meaning if the concentration, if there was more air and the concentration of that fuel fell below that LFL, which is that lower flammability limit, the combustion couldn't occur because the concentration of the fuel would be too low for ignition. So some interesting things to consider there. One other thing to consider is the implications of having humid air. right? Because we're looking at octane, right, which is a major component of gasoline. And we're here in the south, meaning here in the summer, there's a significant amount of humidity going into our engines. So the question then can be asked is, what are the implications of having humid air in our process? Meaning, let's say the air entering can be considered humid, even though this is probably not very humid. And let's say 7% mole percent of that air is now water. What is that going to do? And I'm just asking qualitatively to our combustion process. So now we're looking at that same 8,929 moles of air, but now 7% is water. What influence is that gonna have on our combustion process? What do you guys think?
You'll have to bring more air in to supply the oxygen.
Right, because as the amount of the humidity rises and the amount of water in that air increases, the relative amounts of nitrogen and more specifically oxygen in that air falls. Meaning, all right, if 7% is water, that means 93 mole percent is, the dry air. Meaning the amount of nitrogen falls to 73.5 mole percent, and the oxygen falls to 19.5%. All right, and so it suppresses the concentration of oxygen in the air, meaning you have to put more air through. But we already saw, due to this lower flammability limit, that you can't put too much in. Because if you put too much air in, then the fuel concentration is too low to burn. And so it gives some really interesting implications for designing combustion systems, primarily engines and furnaces, right? You see how narrow this window can get, right? Because we can only allow an 18% excess, assuming there's no water, right? If we have pure dry air. But more often than not, there's an appreciable amount of water, meaning we have to design systems that can essentially operate in those narrow ranges. And so what may look like a pretty sizable window oftentimes can be quite small, primarily because of other considerations like the humidity in the air and the limits of ignition from the fuel itself. So some food for thought. I figured this would be kind of a good example on combustion in terms of in a realistic application, in terms of the limitations of actually making it happen. Any questions on that? No questions? All right, let me take a quick look at our schedule. I think I stated next Monday, we'll get started on ideal gases and equations of state. Don't forget, like I said, the homework 3 is due tonight. Your quiz is due next, Sunday on the 7th at midnight. And the midterm will be on the 11th. I will send out a quick, and I'll post it to Blackboard with an email, like a brief study guide on things that you should know and what we're going to cover. We're going to really focus primarily on this chapter 4 material. But if you guys would like another workday on chapter 4 and maybe have me push back things a little bit and maybe start chapter 5 on next Tuesday, let me know. Feel free to drop me an email, because I think I can get through 5 and 6 with a day lost. So it's really up to you guys. But I want to make sure you're comfortable going into the midterm. So think about it. Let me know. Get back to me. Like I said, send me emails. But I think this is probably a good stopping point for the day. And take care, guys. Have a great weekend. And as always, I'll be online a little bit this afternoon for office hours to answer questions. Hopefully it's been helpful for some of you. And if there's anything I can do to help you this semester, get through the material, learn the concepts, and master these things, let me know. I'm here for you guys, and I wanna help you do well.
Yes, sir. Have a good weekend.
You too. Take care, everyone.